All right, now we're tackling another level of heat transfer following a principle called the principle of heat exchange. It's also called the law of conservation of heat. It's very similar to the conservation law for energy in that it's basically just saying that heat is not created or destroyed, it just transfers from one place to another. So if one substance loses heat, another substance must have gained it. So we're going to do a calculation based on that principle. And this calculation is going to be, we take a chunk of iron, we lower it into water. Iron is at a high temperature, and we put the water at a regular room temperature, so we mix the two together. Now you know from having seen something similar that the iron is going to cool and the water is going to heat up. And that's exactly what the principle of energy, thermal energy exchange, talks about. It says whatever comes out of the iron, whatever heat comes out of the iron is going to go into the water. And heat always transfers from the hotter substance, higher temperature, to the lower temperature substance. So let's have a go at this. The basic equation, the basic way of looking at this is we can calculate the heat transferred first and work it out that way, or we can write out what I just said in equation form, which is delta E H iron, it's going to equal negative delta E H water. All this is saying is whatever the iron, whatever happens to the iron, the opposite is going to happen to the water. An easier way to do this calculation is to say delta E H I plus delta E H W equals 0. And both of these illustrate the point that the water, the heat change, the temperature change, or the heat change of the water has to be negative that of the iron. So if the iron goes up, the water goes down. If the water goes up, the iron goes down. And in this case, we know the water goes up. Now we can break this down. We have our equations for delta EH. We have M iron, the heat capacity of iron, and delta T of the iron, plus M water, capacity of water, delta T of water. And we can take this even further because we actually know the numbers, but let's try and figure out what we're trying to solve for. We're trying to solve for a final temperature, which means we don't have enough here. This equation doesn't get detailed enough. Well, that was fun. So let's bring this up a little bit, give ourselves some room. One thing you're going to find with heat calculations is you need some space to do them until you're very, very efficient at it. Now, delta T equals TF minus TI. And let's call it instead, because we're using I for iron, let's say T2 minus T1. So let's replace these delta T's with that. So MI, CI, P2I minus T1I plus M water, C water, T2 water minus T1 water equals 0. So now we have the value we're solving for in the equation. And I'll point out right now, T2I is going to equal T2W, because I said that heat transfers from the hotter substance, higher temperature, to the lower temperature. Well, if the temperatures are the same, that's when the heat stops transferring. And we're looking for the final temperature. So when the heat stops moving, what is the temperature of the whole system? So those two values are the same. So we can rearrange this a little bit more and say MICI TF minus Ti, where Ti is the initial temperature of the iron, so T1, plus MW C water W TF, notice that I made it the same, minus TW, the initial temperature of the water. Now you don't have to go through all of these steps. Once you're comfortable with it, you should always start. The first couple times you do it, you should start here. Start this way. But you can usually start further down in the equation, depending on what you know of the problem. Next point, next step, we have to isolate for TF. Now this equation right here is the one you're going to find most useful. So it's a good one to have, say, on a cheat sheet. It's a good one to memorize because you can work everything else out from this point. All right, so let's start isolating. In order to isolate for TF, we have to break it out of the brackets using the distributive property. So we're going to get MI CI TF minus MI CI TI plus MW CW TW, TF minus MW CW TW equals 0. So four terms. Now we're solving for TF, so we have to bring the TFs together. So I'm going to circle them here so you can see them or underline them in red. There's the one term with TF, there's the other term with TF. And you'll notice that the other two terms are both negative. And we're going to bring those over to the other side of the equation. If they're negative on this side, they become positive on the other. So we get rid of all our negative numbers right now. MI CI TF plus MW CW TF equals MI CI TI plus MW CW TW. So we've moved our equal sign over to here now. Now isolating for TF, we have to factor it out. So we're going to get TF MI CI plus MW CW equals, and there's nothing we can factor out of the other side, so it's just going to be MI CI TI plus MW, let's make that more clear, MW CW TW. And one more step, TF equals MI CI TI plus MW CW TW divided by this one here, MICI plus MW CW. Now, a quick point, you can't cancel anything on this equation right now. MICI, MWCW will not cancel. That doesn't work mathematically. But this is the point where you have algebraically your final answer. Here, you plug numbers in and solve. Yeah, so at this point, you have one side of the equation is what you want, TF, and the other side of the equation is all the stuff that you already know. You should be able to look up the heat capacity of iron. Ci is 460 joules per kilogram degrees Celsius. And you already know the heat capacity of water, and you're given the rest of the information. So do the calculation, come up with a number, and maybe this time, instead of doing it myself, I'm going to ask you to post your answer on chat and compare with your compatriots in the class. Continuing, 8.5 minutes, a couple more things we can tackle. A simple word version, written word version or spoken word version of the thermal energy principle, exchange principle, is that it's never created or destroyed. Heat only moves from one place to another, and that means that if you've got two substances together that are different temperatures, heat is going to move between them until they're the same temperature. The one that loses the heat energy is going to give it to the other one, and the other one's going to gain. Okay, so read it. It's a little simpler, a little more clear the way it's written than the way I said it. The equation version we just used, these two here. This is the generic equation version. When you have two substances, we won't do three in this course. And you saw how we broke it up in the last video, last slide. Just a couple of little points to toss in here. If 1 and 2 are the same substance, say you mix water with water, what happens to this equation? Give it a try. Same thing if the two substances have the same mass. 10 kilograms of iron, 10 kilograms of water. What happens? I want you to play with this equation. This is your thinking practice. Play with this equation and try to figure out what happens to these numbers, what happens to this equation when things are the same, and see if you can come up with your own version of what kind of things can happen. The other thing I should point out is, if we go back and look at, we went from here, and we simplified from this point on because we wanted to solve for TF, right? What if we wanted to solve for the mass of one of the substances? We need to be able to rearrange this equation, and by the time we get to the unit test, you should have the generic rearrangements done, so you don't have to spend time on that on the test. And it's probably a good idea to check that with a friend. So we have the word equation here, the word version of the principle of energy exchange. We have the equation version of the principle of thermal energy exchange. And finally, I will leave you with the Boromir version. Have a nice evening.